Welcome everyone. Today, I'll be presenting on railway signaling, a crucial aspect of railway engineering. My name is Devanshu Raj, and I'm in my 8th semester, 4th year. This presentation focuses on the signaling systems used in railways, exploring how they contribute to safety and control within railway operations. Railway signaling ensures trains run smoothly and safely, preventing collisions and managing train movement efficiently. Let's dive into the essential concepts behind these systems and understand their importance in modern railway engineering. Railway signaling is essentially the system that controls train movements, using signals, signs, and various devices to guide trains safely along the tracks. You can think of it as the nervous system of the entire railway network, constantly communicating to coordinate train operations. Its primary role is to manage train movements at junctions and along tracks, to prevent collisions and maintain safe distances between trains, which we call headways. Beyond safety, signaling plays a critical role in traffic control by ensuring orderly movement across the network. This helps avoid confusion and bottlenecks, allowing trains to run smoothly and on time. It also boosts network efficiency by optimizing scheduling, so trains can run at higher frequencies without compromising safety. Finally, in the event of emergencies, the signaling system enables rapid intervention, allowing for quick rerouting and managing unexpected situations to minimize disruption. Overall, railway signaling is indispensable for safe, efficient, and reliable train operations. When we talk about railway signaling, there are 3 fundamental objectives that every system aims to achieve, no matter how simple or advanced it is. The first and most important is safety. Signaling systems are designed to prevent accidents and collisions, protect level crossings, and enforce speed limits automatically. They incorporate fail-safe design principles to ensure that even if something goes wrong, the system defaults to the safest state. The second objective is efficiency. A good signaling system helps minimize delays across the network, optimize train turnaround times, and enable precise timetabling. It also reduces dwell time at stations, which is crucial for keeping everything running smoothly and on schedule. Lastly, capacity enhancement is key. Signaling systems allow more trains per hour on the same track, support a mix of freight and passenger operations, and enable both high-speed and metro services. Technologies like moving block systems help maximize throughput by constantly changing train separation based on real-time conditions. Importantly, these 3 objectives, safety, efficiency, and capacity enhancement, must all be met simultaneously. It's never acceptable to improve capacity if it compromises safety. The best signaling systems balance all 3 to deliver a safe, smooth, and high-capacity railway network. Now, let's talk about the basic principles of signaling in railways. Historically, the system used was called the time interval method. Trains were dispatched at fixed time intervals, say every 5 minutes, but there was no guarantee that the previous train had cleared the section. This led to the risk of collisions, especially when a faster train caught up to a slower one. It's important to note that this method is now largely obsolete because of these safety concerns. In contrast, modern signaling relies on the space interval system, which is the current standard worldwide. Here, the track is divided into fixed sections called blocks, and only one train is allowed in a block at a time. A train can only enter when the previous one has fully cleared that block. This ensures a much higher level of safety by physically preventing trains from getting too close, effectively eliminating the collision risks inherent in the older system. To summarize, the transition from time-based to block-based control marked a significant advancement in railway safety, making the space interval system the foundation of modern railway signaling standards around the world. Here we have the main types of signals used in railway operations. First, hand signals, which are given by railway staff on the ground. These are crucial in situations where fixed signals aren't available, such as emergencies, construction zones, or during shunting operations. For example, a red flag means stop, while a green flag means proceed. Next, we have fixed signals. These are permanent trackside structures, like semaphore arms or color light heads, and they're the most common type in modern railways. They are usually controlled from signal boxes or centralized control centers, ensuring smooth train movement across the network. Finally, audible signals play an important complementary role, especially when visibility is poor. These include whistles, bells, and horn codes, each with standard meanings used at stations, crossings, or during emergencies. Together, these three types of signals form a comprehensive system to maintain safety and efficiency on the rails. Let's talk about the classification of fixed signals and stop signals. First, fixed signals are divided into three main categories. Stop signals, indicated by red, either authorize or prevent a train from entering a specific block section. They show red for danger when entry is not allowed, and green for clear when it's safe to proceed. Next, distant signals provide an advance warning of the stop signal ahead. They display yellow to caution the driver that they should prepare to stop, or green when the track ahead is clear. Finally, subsidiary signals are supplementary and are used in more complex areas like shunting yards or for calling on and other specific purposes. These help manage more detailed train movements. Now, focusing on the three main stop signals you find at stations. Firstly, the home signal, marked with a red aspect, is located at the station's entry point. It protects the station from incoming trains and must be clear before any train enters the station limits. The starter signal is placed at the departure end of the platform. This signal controls train departures and only clears when the block ahead is free, ensuring safe movement out of the station. Lastly, the advanced starter is situated just beyond the starter. It's the last signal before the open block section between stations, authorizing trains to enter that block safely. Understanding these signals and their roles is crucial for maintaining smooth and secure railway operations. Distant signals play a vital role in railway safety by providing advance warning of the stop signal ahead. They are strategically placed about 1,000 to 1,500 meters before the stop signal, which is especially important for trains traveling at high speeds because they need ample distance to brake safely. One important thing to note is that distant signals never show red. This is because they don't have the power to stop a train by themselves. They exist solely to warn the driver of what lies ahead. The distant signal is always linked mechanically or electrically to the home signal, meaning it can't be cleared independently. Its indication always reflects the status of the upcoming stop signal. When the stop signal is clear, the distant signal shows green. This means the train can proceed at normal speed without restrictions. However, if the stop signal is at danger, the distant signal displays yellow as a cautionary alert, signaling the driver to prepare to stop at the home signal ahead. Visually, semaphore distant signals use arm positions to convey these messages. A horizontal arm at 0 degrees represents caution. The signal is on, and the driver should prepare to stop. When the arm is angled down at about 45 degrees, that means clear. The signal is off, and the train can proceed normally. Understanding these signals and their meanings ensures safe and efficient train operations. Here we'll discuss two critical safety mechanisms in railway operations, the interlocking system and the block system. Interlocking is essentially a safety arrangement designed to ensure that signals, points, and locks operate only in a safe sequence. This prevents conflicting routes from being set at the same time, either physically or logically, which is crucial to avoid accidents. For example, interlocking stops signals from showing a clear aspect if the points are set for a conflicting route. It also guarantees that the track geometry is safe and derailment-free before a signal allows a train to proceed. There are different types of interlocking technology reflecting their eras. Mechanical interlocking, which involves lever frames and physical locking bars, was common from the 1850s to the 1950s. Electrical interlocking uses relay logic and electrical circuits and has been in use since the 1920s. The most modern type is electronic interlocking, which relies on computer-based systems and solid-state technology, supported by visual display units, and has been around since the 1980s. Now, turning to the block system, this involves dividing the track into sections, called blocks, each controlled by signal boxes. Within these blocks, only one train is allowed at a time to maintain safety. The absolute block system is manually operated between adjacent signal boxes. A train receives a line clear only after the previous train has safely arrived and been confirmed. This system is widely used on Indian railways, where communication happens through bell codes and needle instruments. In contrast, the automatic block system operates signals automatically using track circuits that detect train presence. This system requires no manual intervention and supports a higher frequency of trains. An occupied block is indicated by a red signal, while an unoccupied block shows green. Together, these systems play a vital role in ensuring safe and efficient railway operations. Let's talk about track circuits and modern signaling systems. Track circuits are fundamental for automatic train detection, and they operate on a simple yet effective principle. When a train leaves a section of track, the circuit is energized, and the relay drops to indicate a green signal, meaning the track is clear. However, when a train occupies the track, the wheels create a short circuit, which interrupts the current and causes the relay to drop, signaling red. This setup not only detects trains without any manual input, but also identifies broken rails, as no current flow means the track is occupied or damaged, ensuring a fail-safe operation. Key components in this system include a battery or power source, insulated rail joints to separate track sections, and a track relay that monitors current flow. Moving to modern signaling, automatic signaling systems update signals based on real-time track occupancy, significantly reducing human error and supporting the high-frequency operations seen in metro systems. Centralized Traffic Control, or CTC, takes this a step further by allowing all signals and points to be managed from a single, central location. Controllers can monitor the entire rail network through video display units, enabling quick rerouting and conflict resolution to keep traffic smooth and efficient. Finally, cab signaling provides speed and movement instructions directly inside the train cab, removing dependency on line-side signals, which is critical for high-speed trains traveling over 200 kilometers per hour. This system works hand in hand with advanced safety technologies like automatic train protection and the European Train Control System, ensuring safe and efficient operations at the highest speeds. Let's dive into train protection and warning systems, which are crucial for railway safety. These systems step in automatically if a driver misses a signal or speed limit, helping prevent accidents. Looking globally, Europe uses the ETCS or ERTMS system, covering over 50,000 kilometers. China employs CTCS on more than 40,000 kilometers, and India is expanding its indigenous system called Kavach, currently covering over 2,000 kilometers. Now, understanding signal references is vital. The station layout follows a sequence: distant, home, platform, starter, and advanced starter signals. Block instruments indicate the status of track sections. Line blocked means a train is there. Line clear means permission to enter. And train online confirms a train has entered the section. Semaphore signals are traditional but still informative. Horizontal at 0 degrees means stop or danger. 45 degrees below is caution. And vertical at 90 degrees signals clear. In the UK, AWS uses a horn or bell to warn drivers of a distant signal, applying brakes if not acknowledged. TPWS triggers brakes automatically if a train passes a red signal, known as a SPAD. India's Kavach system is SIL4 certified and works effectively even in zero visibility, preventing collisions. UTCS in Europe uses balise-based communication for continuous speed supervision and cab signaling. Lastly, the color codes on signals are essential. Red means stop immediately. Yellow warns to prepare to stop. Double yellow indicates preliminary caution, signaling the next might be single yellow. Green means proceed at the permitted speed because the line ahead is clear. Understanding these systems and signals helps ensure trains run safely and smoothly.